Infrared spectrum is an important record which gives sufficient information about the structure of a compound. Unlike ultraviolet spectrum, which comprises of relatively few peaks, the infrared spectrum consists of a number of absorption peaks from which a lot of information regarding the structure of the organic compound can be known. The UV visible region consisted of electromagnetic spectrum in the range 400 to 800 nanometer, whereas infrared region covers the wavelength from the range 4000 to 400 wave number centimeter per centimeter inverse. Absorption of IR leads the molecule to a higher excited state. Absorption of infrared radiation is a quantized process. This region encompasses stretching and bending vibration frequencies of a bond in most of the covalent molecules. The frequencies matching the natural vibration frequency of a molecule are absorbed, and an increase in amplitude of vibrational motion of the bond is observed. Only those bonds that have dipole moment that changes as a function of time are capable of absorbing IR radiation. Symmetric bonds, as in case of H2, Cl2, etc., do not absorb IR radiations. Infrared region goes from 4000 to 400 wave number. For an organic chemist, the main region of concern is between 4000 to 400 centimeter inverse wave number. It is in this region that the changes in bond of an organic molecule occurs. The absorption of infrared radiation occurs, which causes an excitation of the molecule from lower to higher vibrational levels. Each vibrational level is associated with a number of closely spaced rotational levels. The infrared radiation is considered as rotational vibrational spectra. All bonds in a molecule are not capable of absorbing infrared energy, but only those bonds which are accompanied by change in dipole moment will absorb an infrared region. A change in dipole moment is responsible for absorption of energy in the infrared region. The vibrational transitions which are not accompanied by change in dipole moment are not able to absorb in infrared region. In infrared spectroscopy, the absorption energy brings about predominant changes in the vibrational energy, which depend upon the masses of the atom, the strength of the bond, and arrangement of atoms within the molecule. It is found that no two compounds, except the enantiomers, can have similar infrared spectra. There are several changes which are responsible for causing an absorption band in the infrared region. Atoms in a molecule are not held rigidly. The molecule may be visualized as consisting of balls of different sizes tied with the springs of varying strengths. The balls and springs correspond to atom and chemical bonds respectively. When infrared light is passed through the sample, the vibrational and rotational energies of the molecule are increased. Two kinds of fundamental vibrations can occur. They are stretching and bending. Again, the stretching vibration can be of two types. That is symmetric stretching, in which the movement of atoms with respect to a particular atom in a molecule is in the same direction. In case of asymmetric stretching, one atom approaches the central atom while the other departs from it. In bending mode of vibration, there may be in-plane bending and out-plane bending. In scissoring motion, the two atoms approach each other. In rocking, the movement of atoms takes place in the same direction. In wagging, the two atoms move up and down the plane with respect to the central atom, while in case of twisting, one of the atom moves up the plane while the other moves down the plane with respect to the central atom. The value of a stretching vibration frequency of a bond can be calculated by means of Hooke's law, which says that frequency is directly proportional to 1/2 pi under root k upon mu, where k is force constant of the bond and mu is the reduced mass. Or in other words, frequency is equal to 1/2 pi c under root k upon mu. For a single bond, the value of k is approximately 5 × 10⁵ gram per second square. It becomes a double and triple for a double and triple bond respectively. The infrared light is absorbed when oscillating dipole moment interact with the oscillating electric vector of an infrared beam. Only those vibrations are infrared active which are not centrosymmetric, as most of the functional group in organic chemistry are not centrosymmetric. This technique is most informative for an organic chemist. The symmetry properties of a molecule in a solid can be different from those in the isolated atom. The vibrational motion resembles the motion observed for a ball attached to a spring, that is, a simple harmonic oscillator. A chemical bond can be visualized as two balls attached to a spring, but it differs from this system since in infrared, certain vibrational levels only are allowed in a molecule. Assuming that all vibrational bands are equally spaced, the energy of overtones is given by E is equal to h nu. For a polyatomic molecule, there may be more than one fundamental vibrational absorption band. The number of these fundamental bands is related to degree of freedom in a molecule. The number of degree of freedom is equal to the sum of coordinates necessary to locate all the atoms of a molecule in space. For an isolated atom, it has only translational degree of freedom. But when an atom combines to form a molecule, the number of degree of freedom are lost. There may be, for a polyatomic system, there may be translational, rotational, and vibrational degree of freedoms. And the total number of degree of freedoms is equal to 3n. Number of vibrational degree of freedom for a linear molecule is 3n minus 5, whereas for a nonlinear molecule, it is equal to 3n minus 6. For example, carbon dioxide, which is a linear molecule, N is equal to 3. 3 and minus 5 comes out to be 4. Carbon dioxide has 4 vibrational degree of freedom, whereas water, which is a V-shaped molecule, it's again a triatomic molecule, N is again 3. So the number of degree of freedom in case of water is 3 and minus 6. That comes about to be 3. Water has 3 vibrational degree of freedom. Carbon dioxide has 4 vibrational degree of freedoms, whereas water has 3 vibrational degree of freedom. But in carbon dioxide, only two of these vibrational degree of freedoms are IR active, because two of the vibration degree of freedom are symmetric stretching, and they are infrared inactive. This is an example of IR spectra in which the transmittance are plotted against wave number. On x-axis, wave numbers are plotted, and on y-axis, the percentage absorbance or transmittance is plotted. The infrared spectrum can be divided into two: a functional group region, that is of importance for an organic chemist, and it corresponds to the region from 4,000 to about 1,500 centimeter inwards. Whereas the fingerprint region corresponds to the wave number 1,500 to 500 centimeter inwards. The factors which will influence the frequency of vibrational motion are: the frequency is directly proportional to 1 upon reduced mass. Greater the reduced mass, lesser will be the frequency. Likewise, greater the strength of the bond between two entities, more will be the vibrational frequency. Conjugation increases the strength of the bond, and hence the vibrational frequency also increases. Vibrational frequency is inversely proportional to hydrogen bond. And the percentage S character of the bond is directly proportional to the vibrational frequency. Multiplicity of the bond is also affects the vibrational frequency. A stronger bond, that is C triple bond C, absorbs at higher wave number, whereas C single bond C absorbs at lower wave number, as seen in this IR spectra. These are some of the important regions in IR spectra. Bond between hydrogen and the heteroatom. CH bond, NH bond, and OH bond. The electronegativity of the heteroatom increases the strength of the bond between, and thus the increase in wave number is observed. A triple bond between CC and C and some heteroatom is the next region that covers the range at about 2500 centimeter inverse. Below it is the double bond region. The carbon-carbon double bond is weaker compared to carbon-oxygen double bond. Hence, the carbon-oxygen double bond absorbs at higher wave number. Below it is the fingerprint region, which is not of much importance for an organic MS. This region covers the single bond between carbon and the heteroatom. A carbon is a CX bond, that is a bond between carbon and halogen. Carbon and carbon, carbon and nitrogen, carbon and oxygen are shown in increasing order of their absorbing in the wave number. A very important correlation can be derived from this figure and the previous one, this one. Using this correlation diagram, one can easily interpret the IR spectrum. What are the major peaks as in this figure? There is a major peak of OH bond, CH, and then the fingerprint region at the wave number below 1500. The fingerprint region corresponds to mainly CH stretching, whereas OH peak that corresponds to functional group, alcoholic functional group, that is at about 3300 wave number. The OH peak again will come at about 3300. The triple bond will be observed in between 2000 and 2800 centimeter inverse, whereas the double bond region is from 1600 to 2000 centimeter inverse, whereas single bond region is below 1500 centimeter inverse. Thus, IR spectra can be easily be used for interpreting the organic compound. It has several other uses in several other fields. The identity of an organic compound can be established from the fingerprint region, that is the region between 1400 and 900 centimeter inverse. Organic compound is confirmed if its fingerprint region exactly matches with the known spectrum of that compound. It can be noted that the compounds containing same functional group may have similar absorption above 1500 centimeter inverse. The structural determination is another application where IR spectra find its use. All major functional groups absorb at their characteristic wave number. From the data available due to absorption frequencies, the probable structure can be predicted. Infrared spectrum of amino acid exhibits bands for ionized carboxylic acid, and so on. The qualitative analysis of the functional group can be done with the help of IR spectra. The presence of oxygen reveals that the compound, that the group may be OH, C double bond O, C double bond OR, COOH, anhydride, etc. An alcoholic absorption band occurs in the region 3,200 centimeter inwards to 3,600 centimeter inwards. Another important application is distinction between intermolecular and intramolecular hydrogen bonding. The inter and intramolecular hydrogen bonding can be distinguished using IR spectra. The intramolecular hydrogen bond is independent of the concentration, and hence intramolecular hydrogen bonds remain unaffected on dilution, and so absorption band also remain unaffected. Whereas intermolecular hydrogen bonds are broken on dilution, and hence there is a decrease in the bonded OH absorption and an increase or an appearance of free OH absorption. On successive dilution, the intensities of the band due to intermolecular hydrogen bond gradually decreases and finally disappear. Due to vibration of OH groups involved in hydrogen bonding, with increasing concentration of ethanol, the intensity of band occurring at 3,600 decreases, while the band at 3,300 due to hydrogen bonded OH group increases. Study of chemical reaction can be done using IR technique. Ketone forms a strong band at about 1,700 centimeter inwards. When it is subjected to reduction, it forms butane 2-ol, which absorbs at 3,300 centimeter inwards because of the appearance of OH group. Ketoenol tautomerism can be easily studied using infrared spectroscopy. The infrared spectrum of compound containing bands because of ketone, alcohol, and ene bonds can be easily studied. A study of complex molecules can be easily done using IR spectroscopy. Conformational analysis is another area where IR spectroscopy finds its use. Geometrical isomers can be easily deciphered because vibration it is known that vibration is IR active only if it causes a change in dipole moment of the molecule. Also, the intensity of the absorption band depends upon the change in the dipole moment. This technique can be easily used to distinguish between cis and trans isomers. The change in dipole moment occurs in cis isomer, whereas in trans isomer which is a non-polar, there is no change in dipole moment. So these were some of the areas where infrared spectroscopy finds its use.